Okay, welcome back to Advanced Calculus. In section 0, we looked at plotting surfaces from functions of two variables. Here's one that we saw, the hyperbolic paraboloid, which has parabolic curves along the x-axis and upside down parabolas along the y-axis. So we could write an equation for that. We could say z is x squared minus y squared. So how can we have differentiation when x and y are varying? Well, what we can do is look at the kind of curves that you get along a line of constant y. So we can imagine each one of these curves here along a constant value of y, and we can do the derivative of that curve if we keep that value of y fixed. Likewise, if we keep x fixed, go say along x is minus 0.5, we can follow a curve through the surface along y. So we need to write that in a special way. So if we want to fix y and differentiate going along going along x, then we can write that with a curly d. So we'd have dz by dx. So that means x is varying and y is fixed. So what that means is we're going to treat y as a constant, just as if it's a number in the differentiation, and differentiate the x as normal. So if we did that, that would get us to x. And that means the derivative going along a cross-section of constant y through the surface along one of these curves that we see going this way. And we can do the same for keeping x constant. That would be going this way through the surface. So if x is a constant, it disappears there. We have minus 2y. So we call these partial derivatives. And that is essential to everything that we're going to do from now on. The idea of holding one variable constant while you differentiate the other one. Okay, what if we do the derivative of the derivative? Let's do the x derivative of the x derivative. It's just 2. If we do the y derivative of the y derivative, minus 2. Now, because we've got, so we have these second order derivatives. Now, because we've got two variables, we could differentiate the first one with respect to the alternate variable. So if I differentiate dz by dx with respect to y, that would be a second order derivative, but that would be dy second, dx first. Okay, that would be 0 in this case because x would be constant. What about if I did the other way around? So I get the y derivative and differentiate with respect to x. Well, that's 0 as well. Actually, these are the same as each other. So that's an important fact that we use, which is the equality of mixed partials. Yeah. So that is the equality of mixed partials. So we call these mixed partials when we swap the variable that we're differentiating with respect to get the second derivative. So that is that these are equal, doesn't matter on the function. We can have some alternative notation. So bringing that back, the first one, alternative notation, well, if we had f of xy, z being f of xy, x squared minus y squared, function notation, the derivative would be f sub x, f with little x for shorthand, and if it was y, we'd have fy for shorthand. For second order derivatives, we'd have fxx, fyy for these two. That's second derivative with respect to x only, second derivative with respect to y only. And then for the mixed partials, we'd have, for the first one, that would be yx, and for the second one, that would be xy. And we'd have our equality of mixed partials expressed that way. Okay, so far so good. That's what partial differentiation is. And then we can look at how we use it. So coming back to the notes. Next section, partial derivatives. So this is where we're just talking about that and the equality of mixed partials. Down here, the equality of mixed partials. Now, an important fact is chain rule. So let's have a look at chain rule for ordinary differentiation. So for ordinary differentiation, this is pretty much what we're thinking about. We have our graph, x and y axes. I'm just going to draw some function, and when I go from one value of x to another value of x, there's a change, small change, and I can have dy by dx, which would be the gradient at this tangent. So if I draw a tangent line there, the gradient of that tangent line is dy by dx at that point, and there'd be a change in y because of that slope, and there's also a change in y going along the function. So the change in y as we go along the function is roughly the gradient of the tangent line multiplied by how far we've gone across, which is our little dx. It's not exactly that. As you can see here, this is a bit exaggerated here because the tangent line is almost horizontal, so that allows us to exaggerate, but it would be equals if we put, well, there's a little error involved in that. And what we can do is, if we say that x is itself a function of t, so like a parametric equation, so x is itself a function of t, we can divide both sides by a change in t, and as we make that tend to 0, these gradients turn into derivatives. dy by dt is dy by dx, dx by dt, and also the error would disappear as well. And so that's where we get our chain rule, roughly speaking. And we can have a chain rule as well for partial derivatives. And so got that down here. So let's see where that comes from. How do we get there? Well, we're going to have a similar process. But as we move along a surface, we go up in Z. We don't go up in Y, but we go up in Z because there's a change in X and a change in Y. And what we have to do is separate the change in X and the change in Y. So we get two terms, not one term. So how's that going to work? Well, if we imagine first cross-section, let's say the y-axis is perpendicular to the screen, to the whiteboard, then we can look at a cross-section through there, and we can look at gradient of a tangent, again exactly the same as we've just done, but the gradient of that tangent is going to be the partial derivative z with respect to x, and the amount we go up in z, so we'll be looking at how much we go up in z, that'll be that times the change in x going across. That's not enough. We also need to look at it from the point of view of the change in y. So the change in x will get us so far, but then there's going to be a change in y on the surface. So if we just look at the perspective going that way, and there'll be some other shape to the curve looking the other way, so x is now poking out of the screen. We can look at that tangent, and so there'd be a change that we get from there, so we'd have to add on the change to z that you'd get by going along the tangent along that direction, like this. And there'd be some errors associated with that. We wouldn't exactly get the change in z going from point to point. So that's going to disappear when we take the limit, so I won't write it. Divide by dt. Yeah, t is some variable, and we're saying that it's parametric. X depends on t, y depends on t. And we take the limit, and then the gradients turn into derivatives here. Our partial derivatives are just partial derivatives, and that's where we get this chain rule here. Yeah, so we're moving from one point on the surface to another point on the surface. There's a change because we're going along an x tangent, plus a change as we go along a y tangent, plus some error, because it's not as simple as that, but it's a small error. And then as we take the limit, that error goes away, and we replace these finite gradients with the exact derivatives. And so that's our chain rule. Okay, so there's different things we can do with that chain rule. I'm just going to come down to this here in the notes. We can play with the chain rule a little bit. So we can say, okay, let's have constant z. So what we're really going to think about is an implicit function with x and y, which is just going around a constant for z. So a bit like we had the circular paraboloid, constant z would be a circle that would go around. And if z is constant, then dz by dt would be 0. And we can say that x is t, free to say that. And then we can change the chain rule so that the left-hand side is now 0. We've got dz by dx, fine. Dx by dt, well, if we're saying that t is the same as x, that's just 1. So we can forget that. Plus dz by dy times dy by dx. And we can make dy by dx the subject in this by doing subtract dz by dx, dz by dx, divided by dz by dy. So that actually gives us a way to get dy by dx in implicit equation. We can apply that. Let me show you how we apply that. So here's an example. So let's say we've got x y cubed is x squared plus y. Okay, how can we do that? Well, we can make a 0 on one side. We can have x squared minus xy cubed plus y. So then that would be our z is constant 0. So if we say z is constant 0, then that fits in with what we've assumed. And if we just say that, well, x is t, nothing stopping us, then we can use this formula here. So if this is going to be our z, then dz by dx, differentiate with respect to x only. So that's 2x. Y cubed is a constant. So this is a constant times x. So it's just minus y cubed. Y is a constant, that disappears. Let's do the other derivative, the other partial. Well, x is constant, that goes. X is constant, we differentiate y. So it's minus 3x y squared. And y differentiates to 1. Okay, so that's what we've got in the notes. And we can put that together here so that, dy by dx, ordinary derivative dy by dx is going to be minus this one. So I'm just going to swap signs because it's minus. Over the other one, I'll just change the order. There. And that's pretty quick and in one step. There's no need for implicit differentiation at all by using partials. And normally in A-level maths, you use implicit differentiation, make dy by dx a subject, but you can do it in one step here. Didn't need to write these steps here. I could have just done dy by dx and then do the partials straight off into the fraction. So that's quite a nice shortcut if you want dy by dx. Okay, so I hope that makes some sense. So I explained what a partial derivative is. And that is fixing one letter and differentiating with respect to the other letter. There's notation like this, shorthand, which saves you doing a lot of writing. The chain rule for ordinary derivatives we've got, and there's also the chain rule for partial derivatives when you've got two variables, x and y. In the appendix, you can see chain rule when there are more variables than that, but we'll stay in the main notes with two variables for now. Okay, so there are some exercises to do, and you need to complete those and return them for marking. So first question, just work out partial derivatives for practice, and showing a result here, equality of mixed partials for that situation, and then finding the derivative of z with these parametrics, and find ordinary dy by dx for this implicit equation. Do it the A-level way with ordinary differentiation, then do it with the chain rule with partial derivatives, and try using the chain rule to prove the derivative of x to the x, which we can do with this method, and then a little bit more working out, use the quotient rule with partial derivatives with this quotient. To prove this result, you need to work out all the derivatives to sub in to prove that the left is the same as the right. Okay, so that's all until next time.